in some of the notes, it actually had a question mark at the end of it. That wasn't intended to be part of the title. That was me asking the organizers whether, is this title okay? And somehow the question went, gave it kind of an edgy kind of, well, are we having initial exploration? Anyway, so we'll sort of see how this turns out. So the topic, to give a little background about myself, I'm in the computer science department at Rutgers. I'm interested in creating algorithms that learn how to behave. So to do this, I focus on the problem of modeling environments, making programs that model environments, and I get to design the learner. And in some ways, this is sort of backwards from psychology, right? So a lot of times the way that you set up a psychology experiment is, well, the learner is something that's in the world, and you have to model that learner, but you design environments to try to test and elicit responses from the learner. And we're really coming at it from the other side. One of the topics that I'm particularly interested in is in-principle learnability. So the idea of what sort of things can be learned from data. If we can make algorithms that learn it, that's great. If we can prove that algorithms can't learn it, maybe people and animals can't learn it either. Maybe that's not the problem that they're solving. So I think some of these things actually provide insight and constraint back to the psychological side for understanding human and animal learning. Oh, so there was a video going on behind me. I didn't even say what it was, but this was I probably should because I'm going to refer to it. So this is basically the simplest real-life reinforcement learning task that we've created in the lab. This is a little hard. Yeah, Mike said this as well. It's a little bit hard to see. It's easier to see on my screen. This is an IBO robot. It's programmed it has two different responses, two different actions that it can take, a little bit turning left and a little bit turning right. It can't go forward and backward in this example. And it can see out of its camera basically a histogram of colors, so it has some sense of where it's facing, at least in terms of kind of color fingerprints in the lab. And we give it a +1 reward whenever it sees the pink ball. So it's easy for us to write little programs that detect whether the pink ball is visible to the camera. And so each time it does that, we give it a little +1. And now the learning task is for the robot to figure out how to maximize its reward per unit time. So how does it behave given what it sees to try to get its happiness, which in this case is seeing the pink ball. It's a lovely pink ball. I mean, it's probably not worth +1, but it is rather nice. So that's the setting that I come from. Oh, RL Cubed is the name of the lab, Rutgers Laboratory for Real-Life Reinforcement Learning. So we focus now. This may not make sense if you have a psychology background, but from the computer science background, there's a whole field that studies reinforcement learning, and by reinforcement learning, we mean tasks like this. We don't mean a particular kind of algorithm or particular kind of neural architecture. We're talking about solving problems that involve maximizing reward. But the thing is, a lot of the research in the field has focused very much on making simulations and then making algorithms that work in those simulations. So the real life part is, well, we're going to try to put this on robots and really learn off of real data. Most of the machine learning community, most of the machine learning field, and you heard some of this in Mike's talk yesterday, looks at really interesting data, gene expression data, and all sorts of interesting things like that. Unfortunately, the reinforcement learning community, even though the problem that they're attacking, that we're attacking, is very real world and very interesting, almost all the research focuses on little simulations, little fake worlds to learn in, little toy worlds. And so this is a toy world too, but it's a toy world where the data is actually real. We're actually getting information from the camera, we're sending commands to the motor, and we're trying to see how that changes the problem and where the difficulties are. All right, so I added this slide because I thought people seem to like the math here. So here's the math. Mostly the models that we assume the fundamental models, the formalism that we use for understanding these kinds of tasks is to formalize them as Markov decision processes. So if you're not familiar with that, the Markov decision process, it's an old model back to the 50s at least. There's a set of states and actions, and at each time step t, the agent's informed of what the current state is of the underlying process, and it gets to choose an action. It then receives a reward from the environment, and we're going to say that the expected value of that reward is RSTAT. And then there's some probability of making a transition to any possible next state. So T, ST, AT, S prime is, if it's currently in state ST and it takes action AT, this is the probability that the next state that it's going to encounter is S prime. So it's a discrete time, discrete space, discrete action, Markov chain. How do you decide how to behave in an environment like this? Well, if you know this reward function and this and the transition function, you can set up a system of equations that are known now as the Bellman Equations that say, well, all we need to do is we need to know the quality the Q value, for being in some state S and taking some action A. We're going to define that as the immediate reward that the agent gets. If it's in that state and takes that action, it gets some immediate reward, but then it also makes a transition to another state and could get more reward from there ultimately. So we're going to discount the future reward by some factor gamma, and the expected future reward is we're going to sum over all next states, the probability of reaching each of those next states, and then the value of the state that's reached, which in this case is going to be, we're going to max over all possible actions, take the action that has the highest quality, the highest Q value in the resulting state. So this is a recursive set of equations, but it turns out you can prove that it has a unique solution, and there's many different algorithms that can be used to solve this that scale pretty well with the number of states and actions. But once you've done this, if you can find this Q function, then the optimal behavior on time step t, take the action that maximizes the Q value for the current state. So once you have this table, it's a simple matter of just what are all the different things I could do, which one has the highest Q value, go for it. All right. So this is all well and good. This is very nice, and it's a very sensible way of setting up the problem of what it means to behave sequentially or behave in an environment where rewards are delivered in sequence. In the reinforcement learning setting, the difference between this setup and what the field of reinforcement learning studies is an agent is plopped into a world and it doesn't know R or T. It does not know the reward function. It does not know the transition function. And yet it still has to somehow act. And so what it's going to need to do is experiment. It's going to need to try actions in the world and gather information about what those actions do so it can ultimately start to behave well. So this is kind of a behavioral learning problem in mathematical form. How are we on this? Is that okay so far? I can just keep going from that. Is this all well known to everybody? In which case I should probably, yeah, okay, sorry. Thank you for your tolerance, though. All right, so then you probably can see that this find the ball problem, you think about the robot as a number of different angles. Those become the states of the Markov chain, and the actions become the transitions. The actions that the robot can take become the actions in the Markov chain. And then the rewards, in this case, the rewards are basically 0 everywhere except for where it could see the pink ball. That state we mark as being special. And so from the Markov decision process standpoint, the world looks kind of like this. So generally, when we embed our learners in environments, we have to write some software that connects up whatever the real-world sensors and actions are to some kind of internal representation that's more like a graph.
So is there any cameras as a sensor that the robot can see your color?
Yes, yes. So the camera was being used for two things in the example that I just showed. One was it was representing the state not as a state identifier, but as kind of a state fingerprint. So basically, what's a histogram of colors that it can currently see? Which is kind of, what does this current state look like? Ideally, you should really detect shapes and so forth, but there's other people who study vision. I'm not any good at that. But the other thing is we actually use that for the reward function as well. We had a little piece of code that just would scan through the image and look for pink. And if there was pink, it would give a +1. Otherwise, it would give 0. Right. And I think from an animal learning standpoint, if you think that, and I do think that that people and animals have some amount of this kind of learning going on in them, an interesting question is, how is this reward function being calculated? There actually has to be something that transduces sensor information into rewards, not just into sensor information. Right? It's not just I need to understand the world. It's that there has to be some kind of low-level reward delivery process. So it could be, some things feel nice, but there has to be some computation that actually computes that that's a good thing, and this is a bad thing.
Design the states has to be designed. You have to know what it is. So why don't you use the distance towards the ball as part of
right. So in different experiments we do different things. So in this particular experiment, we didn't know the distance to the ball. We just needed something that we could compute directly from the sensors. In other cases, we actually take the camera, instead of using the camera at the end of the dog's nose, we have an out-of-body experience. We mount a camera in the ceiling and we detect where the dog is, the robot dog, and then we use the X, Y, and theta as the state. That's a very nice state representation for these problems.
So the definition of state is such that it can give you as much information about what direction.
That's right. Yes, we want to pull that information in so it can use it to make decisions, but not be overwhelmed by it. And that is a difficult problem. All right, so there's different ways of actually attacking this problem from an algorithmic standpoint. The problem is just I need to figure out how to behave to maximize reward. But you could think of the most direct way of doing this is what's called policy search. This idea that what's going on inside the head, the brain of the robot, is basically just some function pi, which maps states to actions. When I see this, I do this. And you can imagine searching for good policies by, I don't know, maybe guessing one or doing hill climbing or something like that, and then evaluating it, trying that in the world for a while and see how it works out. So it's a sensible thing to do. It turns out to often be very, very slow. What people in the community do is something more like what you think of as being reinforcement learning. So instead of trying to learn this mapping directly, it tries to learn the quality function, the Q function, that's mapping when I'm in this state and I do this action, what's my long-term benefit going to be, assuming that I behave optimally after this first action. It doesn't get direct information of this, just like it doesn't get direct information of this, but maybe it can be approximated, and I'll show you how to do that in a moment if you don't already know. But if you have this Q function, you can use it to behave by just always taking the action that maximizes the value. So if you could learn this, you could use it to actually make decisions in the world. The kind of approaches that I tend to focus on are known as model-based approaches. Here the idea is what the robot learns is a mapping from where it is and what it does to where it ends up and how good that was. So it learns this direct sort of one-step information, one-step mapping, which is directly available in the experience, right? As it's moving in the world, it gets to find out, hey, what happens if I do this? There's a training example. But to go from this to actual behavior, there's another step. You actually have to basically solve the Bellman equations to decide how to turn this notion of one-step transitions and rewards into long-term values, and then one more step to turn that into behavior. So, but lots of people work in different places in this diagram. So, yeah.
To understand the point, it would not be possible for the robot to learn something a little magical, like he's looking for the best thing to do. And the best thing to do may be the red light, and then turn right, and then go back to the red light without getting stuck there. The model doesn't permit that.
Because it's not Markov? Is that what you're saying? Because
Markov would be Markov too.
Oh, no, then it could learn that.
So it would get stuck into some kind of magical behavior.
If it's, wait, I'm not sure I follow. We try not to program magic into them generally, but what's that?
That's what's going on.
Okay, all right. I'm interested to know what you mean by that. So one of the most popular algorithms for approaching these kinds of problems, but this is ultimately not going to be the one that I'm going to tell you I like, but it's still kind of cool to know it, is Qlearning. Qlearning goes like this. As the agent is acting in the world, it's getting experience that looks like this. I was just in this state and took this action. I ended up getting this reward as a result, and I ended up in this state after that. What it's going to do is actually keep its own estimate of the Q function, which is going to be wrong at first. But each time it takes a step in the world, it's going to do a little update. It's going to change it a little bit. And the update looks like this. This is not the real Q function. This is a cartoon version that's inside the robot's head. So I used a cartoon font. And so it's going to take the Q value for the state action pair that it just visited, and it's going to update it by adding a little bit, this is a learning rate, a little bit of the immediate reward it got, plus the discounted expected value of the Q value that it ended up in. And it's going to basically push the value a little bit in that direction. What's cool about this, two things that are really cool about this. One is, it's hard to imagine a smaller algorithm for learning in complicated environments. I could have put it on one line with a slightly smaller font. So it's basically a couple lines of code. And it has the property that if each state and action are visited infinitely often, if it explores the world forever, and the learning rates decay but not too fast, then it's the case that this cartoon version of the Q function converges in the limit to the real Q function. And therefore it knows the real values of the environment, and it knows how to maximize reward. So that's a cute trick.
So I thought that earlier on you defined that Bellman equation. So if you solve the Bellman equation, you should be able to get Q already.
Yes, that's exactly right.
So what do
You could solve this Bellman equation if you have to know T and you have to know R.
Oh,
And in the learning setting, it doesn't know that.
Okay, so you don't do that the two-step process. You estimate R and T.
That's going to be the next slide. Yeah. So what's cool about Qlearning is that it doesn't have to have that information, and it doesn't even really have to estimate that information. It ultimately uses the world as its own model, and then does experiments in the world and uses that to update its values. Right. So this is what you're leading me a little bit. That's exactly where I want to go. But the scary thing is most of the field is focused on variations of Qlearning. But here's a little demo, a little human learning demo that we're going to do live. Or not. Where'd it go? Oh, here it is. That to me is instructive as far as this issue of what about Qlearning? So we're going to play this game. It's a little hard to see. This is an orange square. This is red. This is green. This is yellow. A little green circle, blue square. Some of the lines are thicker than others. Okay? There are 6 actions in this world. Up, down, left, right, A, and B. And I'll tell you when you're done. Okay? Begin. So I need you guys got to choose actions and finish the game. And that's all I'm going to tell you, other than when it's over. All right, you ready? This is basically what Qlearning is faced with. This is the state. And this is a Markov system. So this is the state, and I told you what the actions were. Each time you take an action in a state, it gets you to a new state. I'll tell you the reward because you'll win at the end or you won't. It's an MVP. So, all right, so let's see how this goes. All right.
What are the actions again?
Basically, up, down, left, right,
Up, down, left.
A and B.
Okay.
I'll do them, and you can see the result. Somebody's got to toss out some actions, otherwise this is going to take a long time. Okay, I heard it. I heard an up. I'm going to do up. I did an up. I did an A. Okay, I did a B. I did a left. Well, let it sink in a little bit. You've heard people. I'm not a psychologist, so when I do human studies, mostly for me, it's exciting to hear the noises people make. So people have made a noise at that point. It's like, let's enjoy that. All right, moving on. So you wanted to go down again. Down.
We're going to get trapped down there.
All right, well, what do you want to do instead? Or maybe you'd like to be trapped.
Us.
I heard up.
Is it your right or our right?
I'm not telling you anything.
That's the one you live as well.
Somebody called right. I did a right. I did an up. I did an up.
Right.
Does that feel good or bad?
It's all 0 rewards so far. So it's all been neutral. This is, they call it latent learning, I guess. Like you might be learning stuff, but you're not getting directly rewarded for any of this. A. Down. Down. Further down. Down. Left. No, I'll let you know. A.
So promising. B.
B. A. Up. 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 Right. B. You've won. Have you played video games before? That was good, you guys. That was really good. There was a couple things that were a little different from some of the other things I've seen people do. But one of the things that was interesting is often, so what just happened, right? So you were basically the orange square. A and B picked up that green circle, and you dropped it off someplace. So A was picking up and B was putting down, and you can carry it around. But notice that you didn't even do B until it was in the right place to drop it off. It turned out the only place to drop it off was the green square that he went to, or that you as a group went to. But he was quick on the draw, so he led the crowd. So why? What were you doing? Why didn't you do B right away? A lot of times people do A and then B and then walk away and leave the passenger there and not understand why. And only later explore a bunch of other things, then come back, pick up the passenger, and then kind of get lucky and move while the passenger's held and then make a noise. Like, oh, okay. And then usually it's pretty much over at that point. It's like, okay, now I've got the passenger. I understand what B does, and I go and put it down someplace. So, all right. So this is interesting, right? So it turns out, well, okay, I'm going to assert that it's interesting. It's interesting to me. I don't know if it's interesting to you. So this was an encoding of a problem that's in the reinforcement learning literature called the taxi problem. You can see why. You're basically being a taxi carrying a passenger to its destination. It has 500 states, the way that it's set up in this example. You didn't take 500 steps to reach the goal. What's interesting is people have now tested this on a whole bunch of different learning algorithms. Things like Qlearning, which I just described, that explored the environment by basically taking actions that it thinks are the right action, but then occasionally trying something random to learn something new. It's on the order of 50,000 steps before it really gets the problem. It really understands how to win consistently, which actually is very good for Qlearning. Qlearning can take thousands or millions of steps to learn much smaller problems. So this problem was basically deterministic. The learning is pretty fast. It's very reasonable. What I'm going to talk about are some other approaches that we've looked at and some other people have looked at that do other things. So I'll talk about flat RMAX. This is one that basically builds a model of the environment. So instead of just updating these little values, making them go up a little bit or down a little bit, it actually starts to build the map. It builds the big graph, and it plans in the graph. And this actually saves an order of magnitude in terms of steps in learning this problem. There's other things you can do as well, though. It's not really just a big graph. There's actually sort of kind of features of the world, like do I have the passenger or not, or which position in the cell am I in? Whereas the states that Qlearning looks at are completely multiplied out, so they're just 500 different random identifiers. If you take advantage of the structure, you can actually bring it down to on the order of 2,000 steps. Towards the end, I'll tell you a little bit about an approach that we've been doing that actually represents the world in terms of objects and things that you do to objects. So one thing that you guys didn't do is run into the wall. You kept going around the wall without really knowing, well, without knowing for sure that you couldn't just walk right through it.
The point over there is that during the process of guessing, we are not told what kind of reward we get.
No, I did. I told you the reward.
Oh, you told it. Oh, hold on.
No. There was 0 reward everywhere except at the goal. So once you hit the goal, I gave you the +1. Yeah. Now you can talk about, in reinforcement learning, we call them shaping rewards. Rewards that aren't really the reward, but that kind of move you toward, so like if you gotten closer, like warmer, 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 right? I could have done that, but I didn't. I don't know if it would have helped much, because people do this remarkably fast. So on average, we've been seeing people take about 50 steps before they just completely get it, and they never make a mistake again. This is, slightly smaller for people who have a lot of video game experience, slightly larger for people who don't. That's, again, this is my non-psychological account of what I'm seeing when I do this informally. But this a method that actually factors the world out into objects and things that happen to objects can learn about, walls in general, you can't go through them, right? Whereas all these other methods don't really get that. They have to learn about each individual wall. Wall 7, wow, I wonder what wall 7's like. But being able to generalize to objects by type actually saves, quite a bit more, but it's still not all the way to, people are bringing a whole lot more knowledge to bear than just that. So that's kind of the arc that I want to take you through. So the model-based MVP learner that I guess some people were suggesting, it looks more complicated on the slide than it really is. So basically the idea is what we're going to do is we're going to estimate the reward function and the transition function by keeping statistics on them. Each time that we observe a we're in a state, we take an action, we observe a transition to a next state, we'll just keep track of how many times we saw each possible next state and use that to estimate the probability. Same thing with the reward. We estimate the average reward by seeing each time we're in this state and we took this action, what's the reward that we've seen on average. If you do that, then you do what you call the two-step process, where we then take our cartoon versions of the transitions and the rewards, not the real ones, because we had to estimate them, and we'll make a cartoon version of the Q function from that. So sometimes they call this indirect learning, because we're learning the Q function by first learning R and T and then solving the system. I didn't mean to give them credit for this. But this also, the cartoon version of the Q function will go to the real Q function in the limit. But there's some stronger things that we can say about this. For example, the simulation lemma says that we don't need a perfect model to behave nearly optimally. If we have a near perfect model, then we can get near optimal reward by optimizing in the approximate model. That's a really useful thing because that means during learning, it actually has a pretty good idea of where the rewards are, except for the places that it hasn't really explored yet.
But is there anything in that formulation that aims at the idea that all walls are going to behave the same?
No, very much not. Yeah, so that's going to be another representation step on top of the MDP formalism. Yeah, all states and actions are at the moment independent. So what I'm trying to set up here is kind of a Goldilocks situation that we want. So Qlearning learns, but it can actually require exponential experience. And that's not good. If you're a real critter who actually is trying to live in the real world, exponential is bad. Exponential in small numbers is maybe not so bad, but it's still pretty bad. The other thing you could say is, well, you know what, since experience is so important, here's what we're going to do. We're going to construct, at every moment in time, we're going to construct the perfect thing to do, which basically takes all model uncertainty into account and says, I'm going to do this, and that's sort of an experiment, and each experiment that I do can have different outcomes, and if the outcome goes this way, then I'll be able to learn this from it. If it goes this way, I'll be able to learn this from it, and you can think forward, possibly very deeply, to figure out exactly what the impact of all the actions are going to be, squeeze the most information out of all the experience, and behave truly optimally under uncertainty. That's not good, because that ends up requiring exponential computation. So it is good because it's sort of the right thing to do, but the right thing is not good enough if you can't actually run it on real hardware. So I would claim that real creatures, or even machines, can't do these things. It can't require exponential experience, and it can't require exponential computation. So we really want something that's sitting in between, something that's going to do a lot with the experience that it's got, but without having to require exponential computation to squeeze it out. And it turns out that you can actually do this, at least in the simple MDP universe, with a relatively simple algorithm. So what we're going to do is we're going to keep a map of all the state action pairs, and we're going to distinguish between known and unknown transitions. So if there's a state action pair that I haven't tried very often on the learner, then I sort of don't believe it yet. And any transition that's not believed is what we're going to assume has high reward. Oh, I don't know what it is, so it must be good. Okay? This has, you can see problems with that. But what's interesting about this is that if you set this kind of learner going, and with some parameter that says, once you've seen a state action pair this number of times, now you've got the ability to estimate it accurately. So it's got that knob, that parameter to it, and we set that parameter, and then we set the thing into the world learning, and what it does is, at each moment in time, it's going to act in a certain way. Sometimes the way that it acts is going to be the right way to act. It really is the right thing for that environment. In other cases, it's going to be wrong, but it's going to be wrong in an optimistic way, and it's going to learn from that something about its model was incorrect. Like it thought something was really great because it hadn't visited it yet, and then it goes and visits it and it's like, oh, that wasn't nearly as good as I thought it was. And so that changes its model, and the model's getting more and more realistic over time, and the behavior's getting better and better. And the total number of times that it takes an action that isn't nearly optimal is bounded by a polynomial in the size of the problem. So it's learning, at least to a computer scientist, this would be efficient. This would be not too much experience, not too much computation, and we're getting near optimal reward out of it. So we've got polynomial bounds on both of those things. Can we learn not by small increments or thinking ahead, but by... Oh, so what this is saying is that one way of learning is to say, well, we're not going to just make little changes over time because that's inefficient in terms of our experience. And we're not going to think deeply ahead about all implications of our behavior because that would be inefficient in terms of computation. So, this, at least in MDP environments, we can get by just saying things that we don't know much about, we should check out. Does that really work? Does that make sense? And so I was very motivated by a paper by Schultz and Bonowitz that they did with kids. They do all kinds of horrible things to kids. It's not really horrible, but it does seem kind of mean. They set up these situations. So one of the things that they wanted to do is they wanted to understand how kids decide what to play with. And is it motivated by deep statistical concerns? Because you watch the kids do stuff and they're hitting their head with it and they're sticking it in their mouth and it doesn't look so smart. It doesn't look like scientific experiment design. And to be able to pull useful information out of a whole world of possibilities, it seems like you need to do something clever. So it turns out that they're much more clever than you might think. So they created a two-lever toy that looks like this. It's a box. It's got two levers. It turns out that if you pull down the right lever, a little toy comes out of the right side, a little duck or something. You pull down the lever on the left, and then a little clown or something pops up on the left. Okay? But they do two different conditions. In one condition, they show the kids both of the levers and toys popping up and down, and then they say, "Oh wait, I've got a phone call. Here, you can play. You can play with either of these two toys, the one that I just showed you, or a new one that you've never seen before." And kids tend to prefer the new thing, which already gives you a hint that maybe there's something to this idea. So they're presented with the two toys, and then the kids, by and large, focus on the new toy and play with that for a little while. That's not surprising. The interesting thing is, if during the play experience that the experimenter did, they always pull the two levers together. They're always correlated. So the kid has never seen what happens if you separate the two levers. The rest of the experiment's the same. Now we leave them with the two toys. What do the kids do? They start playing with the old toy because they don't feel like they've completely, perhaps because they don't feel like they've completely gotten it yet. They haven't experienced all there is to experience of this toy. And they do, ultimately, they mess with it. They don't just go right up to it and start doing the decorrelation. But they do a bunch of things to it that generally include the decorrelation. And so at that point, they kind of learn what the two levers do separately, and now they're happy with that, and they can move on to something else. So doing really good experiment design is intractable, and maybe it's not surprising that kids wouldn't do it, but you can still get a tremendous amount of information about the way that the dynamics of the world works by being motivated to play with or experiment with things that you just haven't mastered yet. Even if you don't play with them very carefully, as long as you know that you haven't seen everything there is to see yet, that may be a good enough hint. So that's really cool. We didn't literally do this experiment or do models of this experiment or anything, but it's motivating, and it was really interesting to us because we had an algorithm that was very sensitive to correlations in particular, and so it was just funny to see, oh, maybe that was actually a very reasonable thing to be paying attention to. All right, so let's see where we are. are here. Okay, so I don't think I'm going to say too much about pack learning and so forth. I'd like to kind of move through this. But basically, there's these formal mathematical models that we use to try to describe what it means to learn well from data. And we've been kind of messing with that in our lab a little bit. We made up our own model that we call Qlearning, because the important thing for driving exploration is that the learner knows what it knows. It knows the things in the world that it gets and the things in the world that it hasn't quite gotten yet. And we use that to force exploration by basically making the agent hallucinate high rewards in places that it doesn't have a good model yet, that it knows that it doesn't yet know what happens in that part of the world. But what's nice about this framework is that we can start applying it not to just MDPs, but models that have a lot more interesting structure than that. So we can estimate probabilities this way, but we can also estimate conditional probability tables in dynamic Bayes nets. We can actually learn dynamic Bayes nets, like which parents should you have in the dynamic Bayes net. Dynamic Bayesian is just a graphical model or a Bayesian network where the inputs are essentially the state values in the current time step, and the other level that the arrows point to are the state values in the new time step. So it captures this idea of state transitions. And we can actually learn which conditional probability links to include in the network by using this kind of quick learning framework. We have a K-meteorologist problem, which basically is about figuring out what, if there's a whole bunch of different predictors that are giving you probabilities, you have to figure out which one to believe. And so we can do that efficiently while knowing what it knows and what it doesn't know. Certain kinds of logical functions we can do, but not as many as you can do in the classical machine learning framework. And we can also compose all these in all sorts of different ways. So most of our learning algorithms now consist of like a bottom level that's learning probabilities, and a level above that that's figuring out how to combine them. Oh, I didn't include linear regression is on this list as well. We can quick learn linear regression so that it makes linear predictions, but it knows when it's given an input that it can't do an accurate prediction of yet. All right. So just in case that was too much math, here's a video of a robot again. This is a robot that we put, yeah, again, you can, oh, thanks. Yeah, that's great. That's better. This is another IBO robot, later generation IBO robot, and we have it wearing a fetching raspberry beret and a green fanny pack. And because we have a camera mounted above detecting the red and the green circle so it knows where the robot is. So all the decisions that it's making are coming from something that knows the position of the robot in the box. And it's trying to escape. It's trying to get out of the box through this doorway. And it knows it's got 6 actions: turn left, turn right, move forward, move backward, slide left, and slide right. So it could do line dancing, I guess, if we wanted it to. And it's got, we discretized the space here into a 15 by 15 grid and 18 orientation, so it's about 4,000 states. So it's much bigger than the taxi problem. And it's also a bit noisier. But the robot is able to learn pretty quickly, like before the batteries run out, how to get out of the box. And the way that we have it doing it is by using this sort of quick learning idea that there's parts of the state space that it understands, or it has modeled those transitions accurately, and there's parts that it hasn't, and there's the goal. So it knows the goal is good, and it knows that stuff around it isn't directly rewarding, but it understands the dynamics there. But there's this huge sort of yellow zone in between that it knows is out there, but it doesn't know exactly what happens there yet, and it treats that as being rewarding as well. And so little by little, it pushes out, and it understands more and more of the dynamics until it can consistently get out through the exit. So that's one example of that. We have other examples too, where we learn, and that's not a real robot. That's a dog. Hang on a second. Okay, there's the robot. So this is a robot, same kind of thing, where we're detecting it from above using the color pattern on its back. And this is a bumbleball, which we're treating as an obstacle. The robot is trying to get to this location, the corner. And it loses a point when it touches the bumbleball. So again, from the camera, we can detect the position of the bumbleball, the position of the dog, and if they're close to each other, we deliver a negative reward. And we deliver positive reward if it gets to the goal, and a small cost for every step taken. So trying to get to the goal quickly. So in this case, it's a 5-dimensional continuous state space. So the robot has x, y, and angle, and the ball has x and y. But we give it a little bit of extra information to help with the learning. We tell it that the dog and the ball are independent of each other as far as transitions are concerned. They matter together for the reward, but not for the transitions. And that the same behavior, the actions behave the same no matter where it is in the state space. So that's really useful, because once it figures out what left does to its state variables, it can apply that same idea to understand what goes on in other parts of the state space. So it's basically forced to generalize those transitions from place to place. Yeah?
Did you say that this is a continuous state space?
Yes.
And you have an unbounded number of states you can be in?
Yes. So what's fun about this is that we learn, so the learning side is not so bad because the experience, you've only experienced some finite number of those states and the finite number of next states. So you have this finite representation of the data. But then for actually planning, you need to consider all state space, the whole state space. So what we do is we discretize for the planning, for deciding what to do. So the learning is done in the continuous space and is efficient in terms of the experience. The planning is actually very inefficient because it multiplies out the 5-dimensional state space and finds optimal paths through that. So that, at the moment, is one of the weaker things about this structure. We can actually learn much harder problems than we can solve effectively on the planning side.
So where do you put the cameras? Is it in front?
The camera is above, it's on the ceiling.
On the ceiling?
Yeah, it's looking straight down so we can see everything. And you'll see that one interesting consequence of that is that the robot has a camera at the end of its nose, but it's not using it for anything. But we look at this and it looks like the robot's walking backwards. But it's only backwards if you think that it's got a front, and it sort of doesn't. It just has an action that goes in the direction of the camera and an action that goes in the opposite direction. So it somehow figured out that the actions that we endowed it with when we wrote the software are a little bit better going backwards. Nobody uses them because you run into things when you're going backwards unless you've got a camera above you telling you what you can see. So it tends to actually use reverse because it's faster. Yeah.
This robot, principally could also wear a microphone to hear the ball.
But it's sort of again, it's got out-of-body sensations, right? So it actually knows exactly where the ball is relative to it. So we wouldn't. It could. That would be cooler, but it doesn't need it.
I mean, if the camera is not on the ceiling, but it's
Yes.
in your eyes, then there may be a blind spot that you don't see.
That's exactly right. And you can get partial information about things using the sound. Yeah, that would be cool.
So what is the dimensional state in this case?
So the state is the x-coordinate, y-coordinate, and angle of the robot as detected from the above camera. The x and y coordinate of the bumbleball, the obstacle, as detected by the camera.
But you have to quantize those
We
states
quantize them
so that
for
you can use
planning.
this.
Yeah, but not for the learning. So it actually learns a model, nice, actually very lovely continuous model of how all the actions work everywhere. But to use that to actually behave in the world, we chop up the world into little pieces and we do the computation. But it's purely computational at that point, right? It doesn't need any new experience to do that. It just requires a lot of cycles.
When you get a continuous state, you won't be able to really transition. In continuous state Markov model.
A continuous state Markov model, yes.
Then from that, for each state you need to define an action. Then
Yes.
infinite number of actions.
No, it's a discrete state, a discrete action space. There's only the 6 actions.
Oh, I see. So you quantize them, say that this group of states will have one state.
Right.
Okay.
That's right. That's right.
What's the input, Kim? What's the input to the system? What is the input?
The input to the system is,
How does it come to it?
yeah, it's real numbers saying the x coordinate of the robot in the grid, the y coordinate of the robot, the angle of the robot.
No, the input to the robot. For the robot.
Oh, we have the whole thing is a robot really, but I think you might be asking, we have a camera that actually detects the scene, and we have software that we wrote, it's not learning software, that looks for this pattern of dots, and it uses that to figure out the x and y and angle of the robot. That piece of software outputs a 5-dimensional vector to the learner, but the perceptual system as it was is hard-coded. Does that make more sense?
Yeah, well, I thought we like.
Okay, all right, sorry. But this is happening at a bunch of different levels, and some of it is part of the learning system, and some of it is part of just the infrastructure software that we need.
Exogenous and endogenous. Is it an endogenous system?
I don't know that term.
Endogenous means that the inputs come from inside.
The inputs,
From inside the system, not from outside.
it's outside the learner, but inside the robot.
Okay.
Yeah, right, so there's like a little homunculus in there that's doing the decision making. It's outside of that, but it's inside the computer system. Yeah, okay. All right, here's just to prove that we don't only do robots. This is a video game called Pitfall from the 80s that I maybe spent too much time on, and now I continue to spend too much time on. But what's cute about this is an example where we're learning with objects. So we, again, the input, the same sort of issue. The input to the overall system is the bitmap of the screen. We have an Atari emulator, and we just strip the pixels off of that. But then we wrote a piece of software that finds blobs of color. And the color blobs are what's given to the learner. So the learner gets to see that there's there's a guy, not a guy, there's something here, there's a ladder, what we think of as the ladder, there's something here, there's something here. And it tries to learn what happens for each of the joystick commands as a function of the interaction of these objects. So if you notice when it's exploring, it does some interesting human-ish, but not quite as smart as humans kind of stuff. But you'll see it, it's on the ladder now, and it's trying up and down and left and right and jumping when it's near the ladder. It's trying up and down and left and right and jumping on the ground here, but it doesn't try at each place on the ground. Once it thinks it understands this bottom level, it doesn't revisit it. It tries to, rub itself against the wall in various ways, and then it gets the wall, and it can leave the wall alone and makes a beeline for the next thing it doesn't understand, which in this case is what happens when it's jumping at the top of the hole. And now it's got that. Now it's like, here's something new, the log. And so it's going to, rub up against the log in various ways and jump on it. And then it ended up finding its way off of the screen, having learned everything that it thinks it can learn. So the next time it plays the game, it jumps over the hole. There's nothing interesting down there. It jumps over the log, and it's done. And it does, well, the undergrad programmed a little happy dance in so that it sort of celebrates at the end. But the basic idea here is that it's learning very much from its understanding of the fact that there's objects, and it's generalizing the dynamics by object type. And that ended up saves a tremendous amount of time. Something like Qlearning would take quite a long time. Someone's actually doing this in the lab right now, and it's really slow.
Unsupervised learning. Unsupervised learning without a teacher. It's learning by itself, right?
So reinforcement learning is generally considered to be somewhere between unsupervised and supervised. So we have a learner that's learning transition dynamics, and it's supervised in the sense that every time it takes an action in the world, it gets to see the result of that. So it gets basically labeled data. It's done by the world. Yeah, it's gathering its own data. Yeah. So it sort of sits in between. It's not supervised in the sense that you think is supervised learning, but it's not unsupervised either because we have to give it a reward function.
Is this a system, are you people talking to people in NASA or Mars robot?
We did work with the Mars people for a little bit until the funding changed. But when former President Bush said we're going to send a manned mission to Mars, suddenly all the money went away from the robot people, and that included me. Bye. There was, by the way, no manned mission to Mars, in case you were wondering. Funding would have been really useful. So there's interesting sort of things that you can do in that setting as well. I'm also interested in like the Roomba. Even like backyard robots would be pretty cool. The backyard is as yet unexplored. All right, so we're very much nearing the end. I want to just very quickly. So this RMAX thing, use uncertainty to generate exploration. We're starting, this cognitive thing in the title was about building more and more rich models. And we're starting to work with non-parametric Bayesian models because that's apparently what everybody talks about these days. And but it seems to be a really nice fit in the reinforcement learning setting. So here's just to make a slightly concrete example. The kinds of algorithms that we're talking about can't say, I know you've told me all states are independent, but every wall I've seen has been painful. Can I just walk around now, please? Right? Because what RMAX will do is it'll smack itself up against every wall that it encounters, unless you tell it all walls are the same, in which case it'll smack itself against one wall and then generalize that everywhere. But there's no in between, right? There's no maybe it's the case that that walls are similar to each other, but let me check out that hypothesis first. It can't form those kinds of uncertain hypotheses. But Bayesian modeling is really good at that. So the basic idea is that we can have a prior that tells us that similarly colored squares behave the same. They're either all barriers or not barriers together, and we can bound the chance that generalization will lead to suboptimality. So it can actually start to act in the world, maybe test out this hypothesis, and if it seems to be valid, go with it. If it seems to be invalid, move away from it before it's completely excluded it. Just to exclude it with high probability. So the basic idea is that basically if you can figure out, according to your prior, that something is very low probability, then it's okay to ignore it. Past algorithms aren't allowed to do that. They have to do well in the worst possible model in the class that they're programmed to deal with. But the Bayesian approach says, we have a distribution over models and really low probability things. Maybe we can just get by without caring about those. So we created an algorithm we call BOSS, which stands for Best of Sampled Set. And it's maybe a step towards this kind of more cognitive reinforcement learning. And what it does is it has some kind of interesting prior about the way that the world works. And each time it needs to act in the world, it pulls a bunch of samples from that prior. And so here's a bunch of ways that the world might work. Let's act optimistically, that's the best part in the B, with respect to that sample, that will encourage exploration, so it won't get itself stuck in some sort of bad part of the state space. Then periodically, it refreshes this sample. And so the algorithm has a specific way of deciding when to refresh, how many samples to create, and how to combine those samples together to decide how to act. I don't have time to get into the details of it, but the nice thing about it is it modularly combines a Bayesian model learner with this kind of overall reinforcement learning decision-making piece. So we can plug in lots of different kinds of priors. So as of last night at 3 a.m. East Coast time, we submitted our very first paper using a non-parametric Bayesian model, in particular one that says, hey, maybe there's clusters of states in the world, that some states act like each other and some states act differently from each other. I'll show you. Here's a concrete example. So here's a little grid world. It starts off in some starting state. It's trying to get to a goal state. And each state has some possibility of slippage. You can go north, south, east, west. If you try to go east, it might slip north with some probability. It might slip south with some small probability, unless there's a wall there, in which case you can't slip. You just stay where you are. So you can think about each position in the grid. The immediate surrounding walls determine what the dynamics are going to be like in that state. And all the states that have the same kind of walls around them behave similarly. So this algorithm doesn't get to see the walls, but it gets to see what happens when the actions are taken in each of the states that it visits. And in this case, what it actually figured out how to do was notice that all of these states all kind of act similarly. That there's kind of a wall, well, what we see, a wall to the north and no wall to the south or east. In this case, there's a one behind it, but it doesn't matter because it never takes that action, so it doesn't hurt it to have clustered these together. By clustering them together, it can learn the probabilities accurately. Any action that it takes in any of those states count as a sample for all the ones in that cluster. Similarly, as it's going down this right wall, these are all states where there's a barrier to the right and not to the left. So it notices that this state is different, but these four are the same. So we don't give it any of that information. It all comes out of it's a Chinese restaurant process. That actually, I guess each of these are tables. Is that the terminology we were using yesterday? So it's able to do that and actually learn. This is a cumulative reward plot. These are the algorithms that are actually using the non-parametric model. These are algorithms that are learning about things independently. They don't do nearly as well. You actually get a big benefit from noticing that some things are similar to each other.
Why can't you assume that you keep on going until you find something wrong, and then at that time you make the
To do the resampling? No.
No, you don't need to learn as you proceed. Well, anyway, I'll talk to you.
Okay. All right. So just to give some wrap-up thoughts, I don't think humans solve NP-hard problems. We don't have that much computational capability. We have a lot, but not unbounded. We also can't wait for exponential data. So algorithms that people are probably running algorithms that are efficient as far as data is concerned and efficient as far as computation is concerned. In the kinds of models that we looked at, a curiosity drive, check out things that are new, turned out to be really important for getting good bounds on both of these quantities, the computation and the experience. So we're happily stealing lots of ideas from cognitive science to try to create better learning algorithms, and we humbly send back, if you think any of these might be useful, we'd be most honored if you found them inspirational. So that's my pitch. I want to thank everybody for inviting me.
Do you ever work in problems where the reward is dynamic so that the conditions of getting the reward change in time? And some algorithms, I assume, scale to that better as trackers than others.
That's right. That's right. So again, we're working a little bit with Randy Gallistel, who's in the cognitive science department at our center at Rutgers, who does these things to rats in the sense that he creates non-stationary rewards for the rats and watch how they respond to them. And we've built algorithms that follow the model he built of rats, and it's been really useful for predicting things like when to spin down the disk drive of a computer. But we haven't really scaled this up to much more complicated, dynamic, multi-state environments yet. It's hard to publish those, but I think it's a really important problem. But it's complicated enough at the moment, even if we assume that the rewards aren't changing.
So is NDP the dominant approach in reinforcement learning?
Much so, yes. There's also partially observable MDPs that some people look at if, for example, if you are doing the camera from the front and there's things behind you that you can't see, you need to reason about the fact that your state information is partial, your observations are partial. And then some people look at game theoretic models. So how do you learn in a state space with transitions when there's more than one actor? There's more than one agent who actually is making decisions. But they're all variants of MDPs.
But I thought in practical application, the size of state space is a huge issue.
Yes.
So I know that I've been working many years ago on spoken dialogue system.
Yes.
On computer, and that at one time the MVP everybody talk about that.
Yeah.
At the end they say, wow, that's
It was too big.
because space is too big. So in practice, what size of space in learning?
We can if we know the transition probabilities, we can solve multi-million state MDPs. So that's not too bad.
Okay. No, but nothing.
You're getting bigger ones than that.
Yeah, we're gonna probably get it out because it depends on task. If
Yeah.
that spoken dialogue, if we just reserve a restaurant, then that task maybe is not bad. But if you want to open up everything, then
Yes.
so that's scalability issue.
There's people working on different pieces of this. There's no one good answer. We can talk more about it later.
The question that I was asking about magic behavior.
Yes.
One among the experiments that we talked about yesterday about rats, one of the most interesting one was where the cat was in a cage, and in the middle of the cage there was a stick, and the stick was weighted, and the cat has to discover that the stick had to be pushed to get the reward. Okay, so the cat would wander around, and they would discover that, but they would discover it in a different way. For example, a cat would discover that the stick would move by rolling on its back, and that's what the cat would learn. And for a while, the cat was rolling on its back because, what part of the recent behavior is relevant? And that could actually be implemented in your case.
Yes.
With the little dog.
Yes.
Right.
So it could get confused, and I see. This is the magical part that it
That's
thinks
right.
the reason that something actually happened is different from the real physical causality.
Right. You have to discover that too.
Right. We do occasionally get interesting things like that, though usually we engineer the state space to minimize it, but it is interesting. But we did do one where the robot had to escape from a darkened box, and to get out, it had to first. There was a glowing light switch and had to go over to the glowing light switch and hit it with its head. And then the lights would come on. At that point, it could turn around and see the door switch to open the door. So then it would go over to the door switch, push that, and open the door and win. But it actually ended up, and that's usually what it did. But occasionally, it learned this thing that said this. It looked at the glowing light switch and used it as a visual marker so that it could back up into the door switch and then open the door and get out. So it never turned the light on, but it used the glowing light switch as kind of its marker. So it wasn't the intended way out, but...
But why minimize it?
Why what? Why minimize it?
Because actually this is a sort of invention.
Yes. Yeah, invention is great.
Yeah.
The hard part is that, at some point you got to run experiments and make a plot and publish the paper. And so my grad students don't like when it gets inventive. It's just hard to write it up. But I think from an inspiration standpoint, it's exactly the most fun part of this, when it really surprises you. Well, like the dog walking backwards in the video was really interesting to me. Another thing that happened is we had a robot that was moving on a bag of sand, and it learned this sort of weird thing. It reminded me of Zoolander, if anybody knows this movie. So Zoolander was a model. He could only turn in one direction until the very climax at the very end. But this robot would always do that too. Like if it needed to turn from here to here, it would go around the other way and go this way. And it learned to do that. It was very consistent. And later we actually analyzed the physical body of the robot and discovered that there was a problem with one of the Legos. We built these out of Legos. The wheel would jam on it when it turned in the direction. So it would very frequently surprise us because it was collecting the data. It knew what its actions did better than we did.
But that's the way mathematicians prove theorems, actually. They go, instead of going directly,
By rolling
they go to
on
a
their back.
theorem already know, which is a detour.
Right.
No.
No, but intuitively, I'm thinking about this, from the other perspective. As long as the camera detected the goal is right there because the color is there, I just simply decide to turn towards directly going there. Would it be faster than anything you have to tell you about here?
What would that mean? I mean,
so
if
you sweep around and then you see where the goals are, right?
Yeah.
It's colored already. So once it gets detected, then you just go straight there. What do you have?
That's basically what it does. Oh, in which task are you talking about? They're all robot. The light switch one?
One of those you're talking about, with the color as the goal. Right? So what's
The pink ball? Seeing the pink ball? That's what it does. It just.
So you don't have to go back, right?
It doesn't have to go back. There's a learning phase where it's actually exploring and it's figuring out what its actions do. But then eventually it gets to the point where, so the graduate student picks up the robot and puts it at a random angle. And the robot wakes up and it's, oh, okay, I know, I'm facing that part of the room. The ball must be over there. Boom.
But once you see, so all you do is turn around to scan first. Once you detect the
No, it's doing better than that. It's actually turning in the shortest direction to get to the ball.
Oh, I see. Okay.
Yeah, and then once it does, then the grad student comes over and picks up the robot and resets it. So the robot doesn't really get to enjoy the ball for very long. But it takes the shortest way to turn to face the ball. Yeah, go ahead.
Well, there are all these kinds of learning that we do that don't seem to be insightful. The implicit learning processes, motor learning and so forth, where you don't seem to be able to speed it up much. And it seems to me that maybe, I'm kind of curious as to whether or not one could model those in a stupider way, Qlearning.
I think this is what a lot of people are doing now, that they're starting to see that it's not a battle between the Qlearning type algorithms and the RMAX or the model-based algorithms. They're both useful, both in robots and in understanding people and animals. That different systems actually seem to be learning different pieces of the problem. So there's work at MIT on they're making a robot that's a bird that can land on a branch, and they're finding that learning the whole model and planning with it is not a good way of doing this task. But more sort of instinct-driven or reflex-driven learning is working great for them. A guy came and visited my department. He says they're putting reinforcement learning on computer chips to decide how to better utilize the like the memory buffers and things like that. There's all sorts of little decisions that a computer chip has to make while it's processing instructions really fast. And they're putting these more like Qlearning type algorithms, really dumb, fast adapting algorithms there that are reflex driven, but they're doing exactly the right thing. And so they're speeding up the chip tremendously. So I think you're right. I think they're really, I shouldn't beat up on Qlearning. I should just say it has its place. It's just that I guess I'm more attracted to these more cognitive tasks where that's just a bad way of doing it.
Have you done any experiments where, I like how the learner could learn what a wall was. Have you tried to put two robots, right? So now one robot has to model the other robot's behavior, and maybe the other robot is something that triggers the reward for the one, not its own behavior. So now it needs to disambiguate that there are other actors in the world whose effects can trigger rewards besides themselves.
So generally that kind of work has gone on in a separate track. There's the game theory type, or the autonomous agents people tend to use models that force the system to understand that there's multiple agents that are doing decision making. But the Bayesian approach could potentially bridge the gap. You could have a prior that says, well, there's some chance that there's other agents, some chance that there's not. And if it's in lots of worlds where there's not, maybe it'll learn to be more like the MDP model. And if it's in worlds that are multi-agent, then it'll learn to be more like game theory. But yeah, there are people thinking about those issues, but not learning that there's other agents, but just learning when there are other agents.
Sort of a related thing, imagine a world where you could learn from other agents? So like,
Right.
Like transmission of information or like imitation, like, oh, that agent discovered that that's a wall. Ooh, I shall use that information.
That's right. So there's a bunch of ways that people have done that. One is learning by imitation by actually watching. Another one is they just beam the Q tables to each other, right? So one robot learns something and it goes, and it goes into the other robot's head. It's like, okay, sure, I get that now.
You can also imagine like sort of the essence
It's harder for rats to do that.
code, right? And so like, there's information loss or gain.
Yes. Yeah. So but computer scientists like to make their own codes. They don't want to leave the robots to do that. They're like, oh, we'll make a protocol. It'll be TCP/IP.
Well, I think this is fascinating. We could probably keep talking, but I think we ought to move on to the next.